In today's lesson, we're going to see how exponential growth and decay models are seen in the real life. So we'll take a look at some real life applications here. Keep in mind that when we look at exponential growth and we had previously looked at compound interest problems, we were looking at how a um, particular year, let's say 1 year, was broken up into big chunks. But when we look at real life information, let's say like population growth or bacteria growth, we don't just wait for like every quarter for, let's say, rabbits to double or bacteria to grow. They are constantly growing. And so because they are constantly growing, we want to use continuous growth in these models. So because we are going to be using exponential growth in a continuous growth model, we're going to use the basic formula of PE to the RT. But you'll notice that we use different letters, and there really isn't any rhyme or reason to it. It's really just saying that A is the amount of things that you have. So that's why we just use the letter A. But it still has the basic formula of A sub 0 e to the kt power. You'll notice how it still has the same basic principle of the formulas. Just know that A sub 0 is like the initial number. And then the k value, we can call the A sub 0 the initial number as if we're talking about like day 0, you know? And then the k value is just going to be your constant. And the growth or decay depends on that constant. We know that if k is a value greater than 1, then you have exponential growth. And if k is a value between 0 and 1, then we know that we have exponential decay. The same thing goes for growth of cells. Again, the same basic formula is there, PE to the RT. But if you just want to give different letters to it, we're seeing that this formula has an N in it because N represents the number of bacteria that we have. So it still has the basic principle of N sub 0 e to the kt, right? It still looks the same. N sub 0 is, again, the initial number of bacteria in this particular case, or of cells in this case, the initial number of cells. But again, it's just the starting number at day 0. How much do you have? And the k value is, again, going to be a constant. And in this case, we see that because k is greater than 0. Actually, let me think here. K is a positive constant. That's right, because k is greater than 0. It represents the growth rate of the cells. If in this particular case k is negative, then you actually have a decay function yet again. Okay, so just keep in mind those properties there. Now, aside from the notes here, we do have another formula that we could potentially use, and I leave it up to you if you want to use this formula. But if you recall, a basic exponential formula looks like a times b to the x. I'm going to model an equation that basically represents this. The idea here is that a represents your initial number, as we always have talked about. But this time I'm going to give this b a particular value to it. This b, we had talked about how this represents either the growth or decay factor. And I'm going to give you some specific examples, actually. So let's say that if we're talking about the number of bacteria or number of people, whatever we're looking at, and we actually had a value of, let's say, 2 in this particular spot there, in that b value, then what that's saying is that the population is doubling, right? And if there were a 3 in there, you're saying that the population is tripling. If you're saying that there's a half in there, then actually, because the b-value is a value between 0 and 1, you're looking at an exponential decay problem. And what you can say is that the population is halved. And so by using these particular numbers, you can actually go with specific examples of how a population is increasing. And then in the formula, the formula will just slightly change. We'll still have a t that represents the amount of time that passes, but now we're going to divide it by n. Okay, so again, I'll try to represent each of these variables here. So t is the amount of time that passes, and n is a new variable now, and basically that's how long it takes for the object to double or triple or halve or things like that, for object 2, and then I'll just put in here how long it takes for it to do one of these things. And I can give you an example of how this formula is used. Basically, you can interchange these formulas however you see fit. If you want to use the continuous growth or decay model, you can. Just know that you'll have a k value that you'll need to solve for. But if you can also use this particular formula, feel free to use this formula as well. I'll show you how that's done. Okay, so let's take a look at example 1. You cannot use this particular example in all cases, but when you can, it's actually very beneficial. It'll save you some time. Okay, so let's take a look at some examples here. Example 1. A colony of bacteria grows according to the law of uninhibited growth, according to the function, and then here it is, where n is measured in grams. So we're measuring this bacteria by weight, and t is measured in days. Determine the initial amount of bacteria. And so since we're looking for the initial amount, just look at that formula, and we can see that represents the 100. And since we want units of measure, this is 100 grams of bacteria. So it's imagining that you're putting a petri dish on a scale, and you measure that on the scale there's 100 grams. You're weighing the bacteria. What is the growth rate of the bacteria? Well, to do that, what we do is we focus on the k value. So because the growth rate is giving us a k value of 0.045, then keep in mind that rate is a percentage, and so we want to change this into a percentage. So we're saying that there is a 4.5% growth rate. Okay? What is the population after 5 days? So since this represents our t value, let's go ahead and plug that in. We're going to say n of 5 is equal to, and then in our formula we have 100 e to the 0.045 times 5. And we simply just put that into our calculator. So let me go ahead and pull up my calculator. And let's go ahead and solve. So I'm going to write in, let's see here. Nope, that's not it. I'll do e to the, let's see here, e to the 0.045. Nope, that's not 0.045. 0.045. And then we're going to multiply that by 5 times 5. Oops, nope, that's not how I do it. Let's go back up. Nope. Oh, okay. So I think I'm going to need to put parentheses here. E to the parentheses 0.045 times 5. And then we're going to take that answer. Oops. You can obviously see I have not practiced using this particular calculator here. We're going to take that answer, and we're going to multiply that by our initial number. I believe it was 1,000? No, it was 100. I'm sorry. It was 100. So I'm just going to take off one of those zeros, and then we get 125.23. Keep in mind that we want to round our answer to the nearest hundredth at the very end. We don't round until the very end. So I want 125.23. That'll be 125.23, and that'll be measured in grams, just like that. How long will it take the population to reach 140 grams? So based on this question, how long is asking us for a time, and to reach 140 grams, that's going to be our final number. So since that's our final number, I'm going to put that in my equation. I'm going to have 140 is equal to 100 e to the 0.045, and then we're looking for t, so that'll be t right there. We'll need to use some inverse order of operations here. Let me change colors here. So we know that to solve for t, we first need to get rid of the 100. So 140 divided by 100 will give us 1.4, and then that's equal to e to the 0.045t. Since we're solving for t, hopefully you all know what to do by now. What you need to do is you need to ln both sides. And by lning both sides, we get ln of 1.4 equals, and then we'll have 0.045t, and ln and e will just simply cancel out. Finally, we need to solve for t by dividing both sides by 0.045. So we got ln of 1.4 divided by 0.045. Let's go back to our calculator. So we've got, I'll just type it in, ln, I hope this works, and ln of 1.4. And then this answer right here is going to be divided by, oh, my memory is terrible, 0.045, that's right, 0.045. 0.045. There we go. And we get an answer of 7.4, and then we'll round this number to the nearest hundredth, so we'll get 7.48 basically. So the time is 7.48, and keep in mind that t is measured in days, so we can go ahead and say 7.48 days, just like that. All right, what is the doubling time for the population? Take a look at this question. Since we're doubling the amount of material we have, what we want is, if we imagine that in the formula we've got the initial amount, let's call it, what do we call it, n sub 0, then we'll want double that at the very end. So 2n sub 0 equals n sub 0 e to the 0.045t. And you can see what we're trying to solve for here again is the t value. So again, you'll have to divide both sides by n sub 0. They simply go away, and that results in 2 equals e to the 0.045t. And then again, you'll want to ln both sides. Same idea here. And then we're going to get ln2 equals 0.045t. Then we divide both sides by 0.045 to get our final answer. So let's go ahead and do that. ln2. Let's just see if I can ln. Nope, it doesn't work. All right, let's just type it in. Why is it doing that? ln of 2. And we're going to take that answer and let's see if I can just do parentheses. Let's see if that works. Divided by 0.045. There we go. And we get an answer of 15.40. So let's go back. And so t is equal to 15.4. And that's the doubling time. So it'll take 15.4 days for the bacteria to double. Just like that. Okay. All right, let's take a look at the next example here. Again, we're using the same basic formula, PE to the RT or NE to the KT, whatever you want to call it. It really does not matter. All right, so let's see here. If 10,000 bacteria are present initially, so we know that the 10,000 represents n sub 0, and the number of bacteria doubles in 5 hours, how many bacteria will there be in 24 hours? Okay, so in this particular problem, we actually have 2 ways to go about this, and I'm going to show you both of those ways. If we start off with the basic formula of n of t is equal to n sub 0 e to the kt, then that's the formula we just used in the previous example. I'll show you how it's done this way, and then I'll show you how we can actually use the other formula I showed you to make your life a little bit easier. Okay, so let's solve it this way first. First of all, n sub 0 is 10,000. We'll put that in there. E to the, and I don't know the k value, so I'm just going to put k here. And since we have a time here is 5 hours, I'm going to go ahead and just put that as t equals 5. And what we know is that because the number of bacteria doubles, if this is 10,000, then the final amount will be 20,000. So let's read this question again. It says that the number of bacteria doubles. There it is, 20,000. And we initially had 10,000. And it doubles in the 5 days. So you can see here what we're trying to solve for is what this k value, what the rate is. And so we're trying to solve for this rate here. I'm going to go ahead and divide both sides by 10,000, and we're just going to make our way into solving for that k value. So we'll get 2 is equal to e to the 5k, essentially. We'll want to ln both sides so that we can solve for k. And then we know that since ln2 is equal to 5k, to solve for k, we're going to divide both sides by 5. And so k is ln2 over 5. Let's go ahead and type that in. So we're going to say ln of 2 divided by 5. And we get an answer of 0.1386. And so I'm going to go back to my notes here, 0.1386, something, something, something. Keep in mind on your calculator, you do not want to round this answer just yet. It is not the final answer. So what I would recommend is that you store this value in your calculator. I showed you how to do that in class. So remember to know how to use the store feature on your calculator. At this point, my formula has now become n of t is equal to, I had an initial population of 10,000, e to the 0.1386, but keep in mind that I stored this value. Maybe store it as a or x or whatever variable you use. And then we have also a times t. So that's our basic formula. I'm going to go ahead and just, let's pretend that we kind of outline this formula here. Okay. All right. So since that has basically addressed our question, now what we're trying to figure out is how many bacteria there will be in 24 hours. So now we simply just plug in 24 into our time times 24, and then you can just solve for that number. So you can see here the operations I need to do. I'm going to go back to my calculator, multiply that number by 24. So I'm going to take that answer and multiply it by 24. I'm going to take that answer and I'm going to e it now. So I'm going to go ahead and say e to the power of my answer. Oh, I forgot to do parentheses again. So I'm going to say parentheses answer times, wait a minute, hold on. Let me go back. So I did 0.1386. I did multiply by 24, right? So I'm just going to do, to the power of answer. That's it. And then I'm going to take this answer and I'm going to multiply it now by my initial population of 10. Oops, it's not working that way. I need to take that answer and multiply it by 10,000, just like that. Enter. And that'll give me my final answer. I have 278,576.18. Let's go back. 278,576. So 278,576.18. I believe that's what it was. Let me double check here. 576.18. Okay. And so keep in mind that since we are talking about how many bacteria, we're not going to be talking about partial bacterias. And so you haven't quite made it to the next bacteria. So we're simply going to say that you have 278,576 bacteria. We're going to round that number down because we didn't get that next bacteria in that span of 5 hours. In 24 hours. Just like that. Okay, so this is basically the first way to do the problem. I'd recommend you copy this down. I don't have a whole lot of space here, so I think I'm going to have to erase some of my notes from previously. Let's just go ahead and erase up here, and I'll work on the second way to solve this on the top. And you'll notice that the first way we did it, it kind of took 2 steps. You'll notice the green and the red. The green, you have to solve for the k value, put it back into the equation, and then solve for the actual number in red. This time I'm just going to use my basic formula of, over here, exponential growth or decay based on how long it takes. So I'm just going to go ahead and write my formula down. Y is equal to a b to the t over n. And let's fill in all the information we know. Okay, so again, as we mentioned, 10,000 represents the number of initial bacteria. That'll just be the a value. Since this bacteria doubles, that's a very crucial piece of information. I can just say that the bacteria doubles. So we say 2 to the power of. And then t is going to represent my time, and n represents how long it takes to double. It takes 5 hours for the bacteria to double. So my n becomes 5, just like that. And now we have a basic formula. All you got to do now is just say, if I want to find out how long or how much bacteria I'll have in 24 hours, I simply just plug 24 right into the t, and there you go. That's your formula. You just put that into your calculator and see what you get. Okay, so let's go ahead and do that. So we're going to go ahead and do 2 to the power of, and then I'll do parentheses to put in my fraction, and my fraction was 24 over 5. Divided by 5. And then I'm going to take this answer and multiply it by 10,000. That's my initial amount. And you'll notice, oh, look at that. We get the same exact number, 278,576 bacteria. So notice how you still get the same results, and you did it in a lot simpler way, just one step, if you use this proper formula. Keep in mind this formula only works if they tell you how long it takes for a bacteria to grow. Maybe it doubles, maybe it triples, things like that. Okay. All right, so let's now take a look at our next page. How long is it until there are 500,000 bacteria? Oh, this is still the same question, so let's go ahead and put in what we know. How long is it until there, this is the final amount. So let's go ahead and put in 500,000 is equal to 100,000 times e to the, and then our rate was the 0.1386. I'll go back. So e to the 0.1386, and then times t, because we're looking for how long it takes. Now I'm going to leave this up to you. You can basically do the same method. At this point, we've done two problems very similar to this. So I'm going to let you tackle this and find the t value. So go ahead and pause the video and work this out. Okay? All right, welcome back. And so now that we have done exponential growth, now let's look at exponential decay. A classic example of how things decay are maybe how radioactive material is decaying over time. If you think about how radioactive material works, maybe let's say we talk about the atomic bomb that hit Japan, right? And so if an atomic bomb had hit Japan, what you often hear about in the news is how that area is filled with radiation, and you have to wait a long time for that material to basically be clear and be free of any radiation, so it's clear for people to safely live there. So let's go ahead and talk about radioactive material here. Obviously, it doesn't have to be to the scale of a bomb. Just basic substances naturally decay. That's how things work. So the formula still has the same kind of premise. It's the initial number times e to the kt, right? That formula never changes. So a sub 0 is, again, the initial number. And k is this time going to be a negative number because this object is decaying. Okay, so that's really all you got to remember. K is negative if it's decaying. K is positive if it's exponential growth. All right, so let's take a look at our example here. Iodine 131, that's just a number on the periodic table, is a radioactive material that decays according to the function given here. So we have the formula already. What's the decay rate of this iodine? You can see here that the decay rate is giving us a K value of negative 0.087. And so when you think about it, since it's decaying, we're looking for the rate, we're looking for the percentage, then we can see that that's actually going down by negative 8.7%. So if you look at the decay rate, you're just going to do 1 minus that. So if we do 1 minus 0.8087, somehow I didn't type in right. Sorry, let me do that over. I'll do 100% minus 8.7%, and we'll get a value of 91.3. So that's the decay rate that is going down. It's decaying 91.3%. Okay, decaying 91.3%. Okay, all right. How much iodine is left after 5 days? In 5 days' time, that's going to be our T. So we can just go ahead and put that into our formula. Since we have an initial sample of 200 grams, I'm just going to go ahead and say A of 5 days is equal to 200 grams e to the negative 0.087, and we're multiplying that by 5. Just plug that into your calculator and solve for that amount. Remember, round to the nearest hundredth. And we're talking about grams, so go ahead and find that value on your own. Okay. When will 100 grams of iodine be left? We're simply saying this is the final number. So 100 equals 200 e to the negative 0.087. And we're looking for when, so that's going to be our t. And again, I think you are pretty adept at solving for this. Do your inverse order of operations and solve for t. Remember that this is measured in days. Okay. All right, let's go on to the next problem. So here it says, Traces of burned wood along with ancient stone tools in a site were found containing 1.67% of the original amount of carbon-14. Again, this 14 is just excess information, just saying that this is on the periodic table here of carbon number 14. And the half-life of this is 5,730 years. Approximately when was the tree cut and burned? So let's go ahead and solve this. Again, we can solve it two ways. I'll show you the first way first. The way we talked about with using our basic let's put a sub a of t is equal to a sub 0 e to the kt. And let's fill in what we know. So since we want 1.67% of the original amount, that's basically saying that you have 0.0167 of the amount is equal to the amount you have, right? We have 1.67% of that amount is equal to a sub 0 e to the, and I don't know this value, it's just our growth rate there, or decay rate in this case, but we do know that it's going to take 5,730 years to get half of the amount. Oh, actually, I'm writing the wrong numbers. I'm sorry. Since this is going to give us half the amount in 5,730 years, I'm going to go ahead and say that this is 0.5 times a sub 0. So let me rephrase that. So we have half of the amount of material, and it's going to take 5,730 years to do this. That means what we need to do is solve for k. So you can see here, we got to divide by a sub 0. We get 0.5 equals e to the 5730k. And to solve for k, we need to ln both sides. And then ln of 0.5 equals 5,730k. And then lastly, solve for k. This is going to be, again, a two-step process like we have done in the past. So solve for k. So ln of 0.5, let's go ahead and do that. ln ln of 0.5. And we're going to take this answer and divide it by 5,730. There we are. And we get our answer there. So that's the k value, negative 1.209 times 10 to the negative 4. I'm just going to say store this number as a, whatever that is. Then remember, we're going to go to part 2 now. We're going to use that k value and put it into our basic formula over here. So now what we have is, again, we want to find out we have 0.0167 of our original material is equal to the original material times e to the, and then this is the k value that we have there, so put that number in there. And we want to find out now when was the tree cut and burned. So we're looking for the actual value of t that gives us this percentage. So now just solve for t, divide both sides by a sub 0. And then we're going to get 0.0167 is equal to, and then what we have now is the, oops, sorry, I wrote that wrong, is equal to the kt. So is equal to that number that we have. I'll just say, store as a is probably not the best letter. I'll just say k here. So that's going to equal to our k times the t, and we got to divide both sides by the number we have in our calculator. Remember, this is a calculator number. So I just take 0.0167, and I'm going to, oh, I didn't ln it. Oh my gosh, so sorry. Ln that, and that'll mean that the k gets brought down. So I'm going to ln this k as well. Oh no, I'm sorry. That's not lning both the k. It is just k. So now I have ln of 0.0167 divided by k. I'm so sorry. Bear with me. And we're going to get the value of t now. Okay, so let's go ahead and do that. We're going to do ln of 0.0167. Let's see here. I'll get this out. And then 0.0167. And that answer is going to be divided by the previous answer that we got. That was the k value. So divided by that number there. There we go. And then we get a t value of 33,829.96. It's going to take quite a long time for this substance to decay down to 1.67%. Okay, so here we are. So that t value, that was quite a large number. We just put that in there, 33,829. 33,829 what number is that? 0.97, 0.97, and this is in years. So it's going to take quite a bit of time. All right, let me show you the second way of doing this, using that same formula we had talked about before, how we have y equals a times b to the t over n. You can see based on the information that we have here, what we want is, again, 0.0167 of our original material is equal to the original material. And since we have half-life, half-life basically means that the substance gets cut in half. So we'll have half to the power of t over n. And I'm just going to go ahead and fill in my variables here. Since we're looking for how long, that is t, and the half-life itself says that we're going to get half of the substance in 5,730 years. So I just put 5730 there. And then from here, I'm just going to go ahead and solve for t. I divide both sides by a sub 0. I'll get 0.0167 is equal to 1/2 to the power of t over 5730. And then what I would like to do here is to bring that number down. I'm going to go ahead and ln both sides. When I ln both sides, I'll get ln of 0.0167 is equal to, and then I can bring down the t over 5730, and that's multiplied by ln of half. And then at this point, I'm going to go ahead and just move my numbers around. In my final form, sorry, it's getting kind of hard to see, I'm going to get 5,730 times ln of 0.0167 and divide that by ln of half, and that should give me my t value. So let's go ahead and type that in. And let me see if I can just go side by side here, so that way it's a lot easier to see. All right, there we go. All right, so I'm going to go ahead and just clear all this. Can I just clear everything? There we go. All right, so I'm going to go ahead and type in 5730 and multiply that by ln of 0.0167, and then I'm going to take this answer, and divide it all by, nope, that didn't work. Take this answer and divide it all by ln of 0.5. Just like that. And you'll notice, yet again, we get the same answer, 33,829 years right there. And so you get the same result there. Just like that. So you can see how you can use this particular formula. If you're talking about half-life, you have half the amount of material. Just put that in your B value. All right, that'll do it for today, everyone.